Take a glass of water. It's the most boring thing you'll see all day. But right now, sitting perfectly still, it is breaking a law of physics. And here's the part that should stop you cold. If this water obeyed that law like almost every other liquid in the universe, you wouldn't be alive to drink it. Here's a rule the whole universe seems to follow. Cool almost anything down, and it shrinks. Freeze it, and the solid sinks in its own liquid because it's denser than the liquid it came from. Melt a metal and drop a chunk of the solid in. It sinks like a stone. That's just how matter behaves. Water breaks that rule, and once it breaks one, it breaks a whole cluster of them. Every strange power it has traces back to a single tiny trick. So we're going to take one long journey from this glass down into a single molecule and back out to a frozen lake. And by the end, you'll see the ordinary thing in your hand was quietly holding the living world together. Now do something you've done 1,000 times without thinking. Drop an ice cube into that glass. It bobs to the top and floats. But stop and really look. By every rule we just learned, that frozen water should be denser than the liquid. It should sink to the bottom. Instead, it floats. What's going on? Water does play along at first. As it cools, it gets denser, just like everything else. But then, at about 3.98 degrees Celsius, call it 4 degrees, it hits its densest point and does something backwards. Keep cooling, and instead of shrinking, water starts to expand. By the time it freezes, ice is about 8 to 9% less dense than the cold water it came from. Less dense means it floats. To understand why, we have to go inside. So let's zoom in past the surface of the water, down and down, until we're staring at a single molecule of H2O. And it doesn't look like you'd expect. 2 hydrogen atoms, 1 oxygen, but they don't sit in a neat straight line. They meet at an angle of about 105 degrees, making a wide, lopsided V. That bent shape matters because of what happens with the electrons. Oxygen pulls the shared electrons more strongly than hydrogen does, so it hogs them. And because the molecule is bent, that pull doesn't cancel out. The oxygen ends up slightly negative. The hydrogen ends slightly positive. One little molecule with a plus side and a minus side. That lopsidedness is the whole story. Now, put a crowd of these lopsided molecules together, and something lovely happens. The slightly positive hydrogen of one reaches for the slightly negative oxygen of its neighbor. It's like they hold hands. Scientists call each handhold a hydrogen bond. Each one is weak, far weaker than the bonds inside a molecule, and they're constantly letting go and grabbing again. But at any instant, there are trillions of them. And together, those tiny handholds give water almost every superpower it has. So watch what happens when water freezes. In a liquid, molecules jostle close together, handholds forming and breaking in a messy crowd. But cool them enough, and each molecule links to exactly 4 neighbors and locks into a neat, open, 6-sided cage. And here's the magic. That open cage holds the molecules farther apart than the jostling liquid did. More space means less packed. Less packed means less dense, so the solid floats. That single, roomy ice cage is the answer to our whole mystery, and it's about to explain everything else. Now pull back out, all the way to a lake in the dead of winter. Because ice floats, the freeze happens at the top. A lid of ice forms on the surface instead of at the bottom. And that lid acts like a blanket. Ice and snow are poor conductors of heat, so they slow the cold coming in, and a deep pool of liquid water, often near 4 degrees, stays alive underneath. Fish swim through the winter just below the ice. But let's be honest, because the truth is better than a slogan. Floating ice isn't a magic shield. A shallow puddle or a thin stream can still freeze all the way to the bottom. What really saves the deep lakes is 3 things working together: the floating lid on top, the sheer volume of water, and water's stubborn ability to hold on to heat. And that last one, it's the same handholds again. And this is the part one love. We don't need a new explanation for anything else water does. That same handholding, the very same trick, is hiding behind all of it. Start with heat. Why do the oceans keep coasts mild? And why doesn't your body spike in temperature the second you start running? To heat water up, you first have to shake those trillions of handholds loose. So a lot of energy goes into the bonds before the temperature even moves. Water resists changing temperature more than almost anything you'll meet. Pound for pound, it takes roughly 5 times as much heat to warm water as it does to warm the same weight of rock, and about 10 times as much as iron. Among the everyday materials around you, water is the standout. Scale that up to an ocean, and you get a planet-sized thermostat. All that water soaks up the sun's heat by day and releases it slowly, which is a major reason coasts have milder swings than the dry interiors of continents. And you're mostly water too. That's part of why your body can hold a steady internal temperature instead of lurching with every effort. The same molecule steadies a whole world and steadies you. Now, look at the very surface. Down in the bulk, each molecule is held on all sides. But at the top, there are no neighbors above, so those molecules get pulled inward and sideways, pulling the surface tight like a trampoline. That taut skin is why a water strider can stand on a pond without sinking. Among ordinary liquids, water's surface tension is one of the highest there is, beaten mainly by liquid metals like mercury. That same clinginess lets water climb up narrow tubes on its own, a trick called capillary action. And you'll often hear it's how trees drink. But on its own, capillary action can only lift water about a meter, nowhere near the top of a tall tree. The real engine is up in the leaves. As water evaporates from them, it tugs on the water below, pulling a single unbroken thread of water all the way up from the roots. And what keeps the thread from snapping? Hydrogen bonds. The handholds hold the column together. And because it's lopsided charged, water can pry apart salts and sugars and wrap around the pieces. It dissolves more kinds of things than any other common liquid, which earned it a famous nickname, the universal solvent. But that's just a nickname, not the truth. Water doesn't dissolve everything. Try to mix it with oil and it flatly refuses. Still, that dissolving power is why water carries nutrients through your blood and every living cell. Now, it's tempting to say water was somehow made perfect for us. But the honest story is more wonderful than that. Water is built from hydrogen and oxygen, 2 of the most common elements in the cosmos, and we find it everywhere, in comets, on distant moons, drifting in the clouds between the stars. None of its powers were aimed at us. They all fall straight out of ordinary chemistry, a bent shape and a lopsided charge. Life didn't get handed a perfect liquid. Life grew up around the strange one it found. So come back up now, out of the molecule, back to the glass in your hand. It looks exactly as boring as it did a few minutes ago. But you know its secret now. The lakes that survive winter, the oceans that steady the climate, the blood that carries life through you, all of it leans on the same small refusal. One plain, everyday molecule that will not behave like everything else. That's why you're here, to hold this glass at all. And maybe that's the most beautiful part. Not a miracle from beyond, but a rule breaker hiding in plain sight, on every table and inside you. We once found you've never truly touched anything, and that the air you're breathing is older than the dinosaurs. Now, the plainest thing of all turns out to be the strangest. The ordinary was extraordinary the whole time. So the next time you pour a glass of water, remember, you're holding a quiet rule breaker that keeps the whole living world alive. If a hidden truth like this just changed how you see something ordinary, go watch how you've never actually touched anything, and how the air in this room is older than the dinosaurs. Subscribe because curiosity has no limits.